All right, so now that we know how to draw Lewis diagrams, we're going to start to figure out what these molecular shapes are in real life in 3 dimensions. So, the name of this process is called the valence shell electron pair repulsion theory, or VSEPR. So, valence shell aspect, we're talking about the valence electrons. We're talking about electron pairs and the fact that they all repel each other. So, first, let's define what we mean. Um, well, actually, here, let's just start with the first shape. Whenever we draw a Lewis diagram, we need to know what a steric group is, or an electron group. So, an electron group can be either a single bond, it could be a double bond, a triple bond, or a lone electron pair. So let's say that we had a pretty simple molecule like this one. Now, if you recall, beryllium is an exception to the octet rule. It doesn't need a full octet. If we add up the electrons for BeF2, we have 2 plus 14. So we've got 16 overall. So we fill up our octets on the fluorines on the outside, and we're actually done. Beryllium has 2 bonds, both to fluorine. Now, in this theory, we're always going to be focusing on what the central atom is. Okay, this whole process is geared around paying attention to the central atom. So, for this particular molecule, when you have 2 pairs of electrons, the pairs of electrons will always spread out to be as far from each other as possible. And that turns out to be an angle of 180 degrees. So, however this molecule turns, if this were to rotate, if this pair were to kind of shimmy over and move in this direction, this other pair of electrons would kind of respond by being pushed away from it. So they're always will settle in a position where they're as far apart from each other as possible, and that means the largest bond angle possible, 180 degrees. So when there are 2 total groups, which means in this case here there's 2 bonding sites, there's no lone pairs, the molecule looks like this, and the name is called linear. Another example of this would be something like CO2. 4 plus 2 times 6, so 12, so 16 again. So when we draw this, we're going to end up needing 2 double bonds to make this work. This shape is going to be linear also. It's got 2 electron groups. The groups just happen to be double bonds, and that's okay. And in order for the double bonds to be as far apart from each other as possible, you're going to have 180 degrees, which means this shape is also linear. The next shape, let's say that we have a molecule like this. 3 plus 21 is 24. So we have 3 bonds, and boron is also an exception to the octet rule. Boron will only have 3 pairs of electrons on it. So in this molecule, 1, 2, 3 bonds. When there's 3 electron groups, the farthest apart that they can be from each other is 120 degrees. So all of these angles here, it's the same angle. Now, the name of this shape is called trigonal planar. Planar means flat, and trigonal because it's like a triangle. So when there's 3 groups, your shape is going to be trigonal planar if they are all bonded. Another example of this, we drew this one earlier in the notes, SO3. And we realize that we are going to have resonance on this molecule. Remember that resonance means the double bond is actually averaged in all of the places that it can be. So while it looks, we'll draw one Lewis structure for the double bond in that direction, one in this direction, and then one more in this direction. But the point is, there are 3 bonding groups, and so these are all going to be, the angles are going to be the same, and the shape is going to be trigonal planar. Our next shape, say something like CH4. We would draw our Lewis structure like this. There's 4 bonding groups. Now, when you have 4 groups, this cannot lie down flat. In order for the electron pairs to be as far apart from each other as possible, it takes on an angle of 109.5 degrees. And because of that angle, this actually ends up standing very similarly to how a tripod would stand. Right? If you can imagine the floor being here, here, and here. So, 4 bonds, 4 groups, 109.5. The name of this shape is tetrahedral. Right? So tetra means 4, hedron means sided. 4-sided. So this shape here has 4 different sides to it. Now this is a 3-dimensional shape. Anything that stands, if it stands, that's what we consider a 3-dimensional shape. This shape here, planar trigonal, is flat. The linear shape is also considered flat. Okay. Sometimes you have molecules that have lone pairs, like ammonia, NH3. So 5 plus 3, so 8. Your Lewis diagram would look like this. Well, here we only have 3 bonds. 1, 2, 3, and you have a lone pair. So because there's 4 groups, the shape of this is still follows the same angle structure as a tetrahedral. The only difference is your electron pair on the top is here instead of a bond. If I drew this, then we'd call the shape a tetrahedral. But this does not actually have 4 bonded atoms. It only has 3 in the lone pair. So the shape is different now. This is what we call a trigonal pyramid, right? Because it's a pyramid with a base of a triangle. It's 3-dimensional because it stands up. There's 4 total groups, but only 3 of them are bonded, and then there's 1 lone pair. So hence the shape looks different than this shape. Well, what if we have 4 total groups, like water, but you only have 2 bonds and 2 lone pairs? Well, your basic electron pair geometry is still that like a tetrahedral, but instead of having bonds, you've got lone pairs instead. So this shape is what we call bent, because from a side view, it looks like a bent line. Now, keep in mind, anything with 4 pairs can never be straight. So it's going to have to be 3-dimensional because it's going to have to stand. 3-dimensional, 4 groups, 2 bonds, 2 lone pairs. So this table is a summary of the shapes that you would need to know. Right? There's 3 families: the 2-pair family, which will be linear; the 3-pair family, which has 2 different shapes. It's got a trigonal planar. This is the basic shape. If one of these was a lone pair, then this would be bent. Your 3rd family, which is tetrahedral, Your first shape is tetrahedral if there's atoms bonded in all four places. But if one of those atoms is a lone pair, then this is trigonal pyramid. And if two of those are lone pairs, this is now what we call bent. So you will need to be able to draw Lewis diagrams and determine which three-dimensional shape, what molecular geometry they're going to have based on how many bonding pairs and how many lone pairs they have. So I'll just do a couple examples here. Let me draw some more. If we had a shape like this, PCl3. First we determine the Lewis diagram, so we count our valence electrons. So 5 plus 3 times 7, 26 valence electrons total. We draw out our shape, 3 chlorines, add our valence electrons. Now at this point I have 8, 16, and 24 valence electrons. The last pair will go here. Now we have, if we count them up, we got 1, 2, 3 bonds, and then we have the lone pair. So 3 bonds, 1 lone pair. That is trigonal pyramid. And so we would write that down. And that's how we go about determining the molecular geometry.